Hello, my name is Carlos Aguilar. I'm a student from Calculus 2. Here I'm going to present my group's presentation for project number 2 along with Scott Berardi and Williamson. The problem today we chose to present is problems. It's a problem from Problems Plus from page 692, and it's exercise number 4. The exercise consists of having 4 bugs displayed on a square. Each one of the bugs is placed on one of the edges, and from there the bugs are moving towards each other at the same rate on a constant velocity. So what are we gonna try to get from this exercise is see how long or what's the distance the bugs would have to walk to reach each other, which would be at the end the same point in the middle because they're walking at the same rate. So first we're gonna start by visualizing the bugs here. Since we know the 4 bugs are moving at the same rate, we're gonna only take into account 2 of them. Here one is the first bug, and here's the second bug on each of the edges. So here, this line, this means the slope that will one bug have after moving a certain amount of time. And as we know, that line could be considered as a slope, which is the rate of change on the velocity or the speed at which they're moving. So here we have the first bug at certain polar coordinate, which we know the r is going to be the distance from the center to outwards, and the angle, which is unknown for us, especially because it's moving at a point. So, and we don't know at which point or what's the velocity at which they're moving. And here we had the polar coordinate for the second bug. Here it's the same as the first one, but plus pi over 2. Why? Because since we know it's on a square, we know each bug is going to be 90 degrees apart from each other. So in radians, this is pi over 2. Then we have the equations taught in class, which are x equal r cosine theta and y equals r sine theta. So now taking this into account, we're going to try to convert these polar coordinates to Cartesian coordinates. And then here we have the first one for bug number 1, which is going to result in r cosine theta as its x point, and its y point is going to be r sine theta. The same thing goes for the second bug. We just substitute the same things, but in this case, instead of only theta, we're going to have theta plus pi over 2. Same thing. Here, we know we're working with polar coordinates, and as we know, these polar coordinates can be represented on many ways. Here we're going to change it to negative r sine, comma, r cosine theta, for the same reason that we know they're going to be the same points with different angles. We're just trying to avoid having pi over 2, which makes the problem a little bit difficulter. Yeah. And it'll make it easier for us to substitute later on the problem. So like I said at the beginning of the problem, we know that the bugs are moving towards each other and at the same time getting closer to the center of the plane. So we know that the change of the rate is going to be equal to m. And as we know, as a bug moves or as a position changes, that's the same as dy dx, which is the derivative. So what we're gonna do is get the slope from these 2 points, considering it as x, y coordinates. And as you can see here, we have y2 minus y1, which is, in this case, this will be y1 and y2. And also x2 minus x1, which goes for the same case of this. Here, by trigonometric identities, we end up with tangent of theta minus 1 over tangent theta plus 1. Now we go with the derivative of dy dx. Here we know that for this case, we're only going to take into account 1 bug because we're trying to acquire the rate of change of one bug only, since they're all walking at the same rate. Since we have the first bug, which is easier than just using negative r signs, we're going to have y equal r sine theta, and then take out its derivative, which is sine theta plus r cosine theta, and also same thing for x equal r cosine theta, and get its derivative. This is, each one of these derivatives is the same. This dy is the same as dy over d theta. So basically what we're going to have here is this is going to go dy d theta over dx d theta. As we know, d thetas are going to cancel out. That's why we can prove that this is dy over dx based on the x and y coordinates that we have. Now what follows is that we know that it's a rate of change, and it's also the slope of how the bug is moving. We can have that dy over dx is the same as is equal to m. So right now what we're going to do is combine these two equations to each other and try to substitute and cancel out factors. So here we have them combined. You know, what's dividing goes multiplying, vice versa. So here's our situation. Due to space, I cannot put them in a single line, but here you can see it. Here we represent that's dr over d theta to let us know that's the representation of what we had earlier as the derivatives. And then thanks to more trigonometric identities, we end up with dr over d theta times tangent square of theta plus 1 equals negative r times tangent squared of theta plus 1. Here, if we cross out, we're going to cancel out tangent squared of theta plus 1, since we have them on both sides. Therefore, we can know that dr over d theta is equal to negative r. Now we move forward, and we can notice that dr over d theta is being equal to negative r is the same thing as a differential equation, which can be arranged like this, equal to 0, as we know. So then we work to solve this differential equation using p theta, q theta, and mu theta. And from here, we're going to find out mu theta is the same as e to theta. Here, we use one of the formulas used during class to learn what's r equal to. And we're going to end up with c over d theta. Now, as we know, c is a constant. So what we're going to do is try to solve for it to later get a result for r equal something, which is going to be our distance, our equation for the distance that we're going to use to get arc length and figure out how long did the bugs have to walk until meeting each other. So from the previous square, we know that here is where bug 1 started, and this is the center where we know they're going to meet up. With Pythagorean theorem, we know that this line is going to be equal to a over square root of 2. So now that we know that this is going to be r, and we just substitute each other. So, since we know this line is going to be pi over 4, we just equal it to each other. Now, what we're going to do is try to clear out c using the angle and the length to figure out what r equals to. So here we have c equal a times e to the theta over pi over 4 all over square root of 2. Now from there we can substitute c on the original equation we got from this problem. And since e to the theta is on the bottom part, we can rewrite it as a negative exponent on top, and we're going to end up with this one. Now, we're going to use this formula acquired to figure out the arc length. As we know, the arc length is the derivative of ds on a definite range. So from here, we know the formula. This is going to be dr over d theta squared and r squared. Now, as we know, dr over d theta is the same as negative r. Since it's squaring, it's going to be the same for both cases, since negative signs cancel out. Since they're the same, we rewrite them together, and now we have 2 times a squared times e to the pi over 2 minus 2 theta. Here the 2's cancel out, and now we end up with this, which is we take the square root of everything, so this 2 cancels out, this turns into 4, and this 2 lives, or it's erased. From here we can just continue with a normal integration as we would do in class. Here we end up with this equation. As we know, a is one of the lengths of the square, so it's a constant. Also, e to the pi over 4 is a constant, so we are going to use them as, we're going to take them out of the equation, and we're going to be left only with 1 over e to the theta, or the same as e to the negative theta. So we substitute the values. We have infinite, which is going until it stops, and we're going to end up with a times 1 over e to the infinite, which, as we know, as a number gets bigger on the denominator, it's going to equal 0. And substituting pi over 4 on this part is going to equal to 0, which is the same as 1. And since we have negative 1 from this sign, we're going to have that negative a times negative 1 is going to be equal to a. So that's the result. Bugs are going to have to walk a distance, the same distance from one of the sides of the square, to meet each other at the center. Thank you for your time.